Dr. D here, and today we're going to go through some exam problems about intermolecular forces. So get out your pencils as we practice, practice, practice. So for our first problem, it states, circle the best description of each molecule, ionic, polar, or nonpolar. Then label the strongest intermolecular force shown for each molecular pair. Finally, rank all 5 pairs in descending strength of intermolecular force, 1 being the strongest, 5 being the weakest. So if you want, go ahead and pause the video and you can figure this out for yourself. And now I'm going to go ahead and go through this. So first thing we want to do is we want to figure out what type each molecule is. So we're looking at this very first one, and we don't see any charges, so it's not going to be ionic. And then all we have are carbons and hydrogens in here. So it's not going to be polar, so it has to be nonpolar. And same is true for the neighboring pair. It's the exact same molecule. So both these are nonpolar. Whenever we have 2 nonpolar species interacting, the strongest intermolecular force between them is going to be dispersion. Then we can look at our second example, our second problem. We don't see any charges, so it's not going to be ionic. And then we have this oxygen here, and so that's going to be drawing the electrons towards that. And so this is going to be an overall polar molecule. And since they're both the same, they're both going to be polar. So we have 2 polar species. So normally we would think this would be dipole-dipole, but we also have it undergoing the formula of HX, HX, where in this case, X is going to be oxygen, but if this is ever nitrogen, oxygen, or fluorine, this would be hydrogen bonding. So that is what this is. This is going to be hydrogen bonding. All right. Now looking at the next one, we see that we have a positive charge and a very small negative charge, but still negative. So both of these are going to be ionic. And so whenever you have 2 ionic species come together, this is going to be ion-ion. All right, for our next one, we have chlorine, which is more electronegative than hydrogen. So it's going to be pulling the electron density over there, making it polar. So since we don't see any charges, it's going to just be polar and polar. All right, in this case, we don't have nitrogen, oxygen, or fluorine attached to hydrogen, so this is simply going to be dipole-dipole. There we go. All right, so we have a dipole-dipole interaction. And then for this final one, we don't see any charges, so it's not ionic. And all we have are carbons and hydrogens. And so it's not going to be polar, so it has to be nonpolar. So both these are going to be nonpolar. And when we have 2 nonpolar species coming together, this is going to be dispersion is our strongest intermolecular force between the 2. All right. So now we need to try to rank these. Now, there's a few things that we can do. And there's a few of these that are actually comparable. So the first ones I'm going to compare are going to be the ones with the exact same molecular weight. So we have this very top one here and this very bottom one here. Now both of these have the exact same molecular weight. They also have the exact same chemical makeup. They're both C5H12. And so now we need to determine which one is essentially has the stronger intermolecular forces. So for this top one, it's kind of balled up, so it's going to be spherical in nature. And for this bottom one, it's a bit more elongated. So it's going to have this kind of pill shape. And so we need to determine which one of these is more polarizable. And again, they have the exact same chemical makeup, so they have the exact same number of electrons. So this is going to come purely based off of shape. And since this kind of pill shape allows the charges to be more distributed or separated, that's going to make this one have a little bit stronger intermolecular forces. So I'm going to go ahead and label this a 1, and I'll label the other one a 2. So I know that A1 is stronger than A2 as far as intermolecular forces go. Now, for these other ones, there's really only one other set that we can say is maybe comparable, and this would be the sodium chloride and hydrochloric acid. So the middle example and the second from the bottom example. I'm going to label these as B. Now the reason why these are comparable is the molecular weight of sodium chloride is a little bit higher, so it has a little bit higher molecular weight. In truth, this just means it has more electrons, so more electrons than HCl. And then the other thing is that it is ion-ion. So an ion-ion interaction is much stronger. An ion-ion interaction is much stronger than dipole-dipole. So it has essentially two things going for it. It has more electrons, and it has one of the stronger intermolecular forces. And so in this case, I would say this is going to be B1, this is going to be B2, and their molecular weights, like I said, sodium chloride has a little bit higher molecular weight, but they're still somewhat comparable. It's not great, but it's somewhat comparable. Now we have water. Now we know that water has some unique properties because it has essentially two sites for hydrogen bonding. So in truth, we can't really compare this with the other ones and get a direct answer. So what we have to do is we have to realize that we need to be looking at the boiling points. So if we look at the boiling points of all these, this is where we're going to be truly getting our ranking of their intermolecular forces, because these are not all directly comparable. It's not comparing apples to apples. I tried to show you a few that we could look at and say, all right, well, we know that A2 is going to be weaker than A1, and that B2 is going to be weaker than B1, but we don't exactly know how they're going to all compare. So we just need to look at the boiling points, and we see that for sodium chloride, that has the highest boiling point of 1,413. So that's going to be the strongest intermolecular force, or pair. And so that's going to give a 1. Then for the second highest boiling point, we have water at 100. So that's going to be 2. Then the next highest one is pentane here on the bottom. So that's going to be given a 3. And then we have 9.5 degrees Celsius for the top one. This is 2,2 dimethylpropane. And so that's going to have a 4. And then lastly, we have our hydrochloric acid with our weakest intermolecular forces of all of them. And this would be hard to predict because it is a dipole-dipole interaction, but it also has a very low molecular weight. So again, this is why we have to actually compare the boiling points. And we can kind of double check our predictions earlier where we have B1 and B2. We can see that 1 is definitely higher than 5. So this still held true. And we can compare our A1 and A2. And 3 is higher than 4, so our predictions were holding true to form, and so this is how you can kind of compare things directly if they are comparable, but sometimes we have ones that aren't really comparable, so that's when you have to definitely use boiling point. All right, so let's move on to another question. All right, order the following molecules in increasing boiling points. So we need to, one, recall that if we have stronger intermolecular forces, this means that we're going to have a higher boiling point. And I'll go ahead and put the vapor pressure will be lower as well. For this one, we don't really need vapor pressure, but just wanted to go ahead and complete out the series. So for this one, we want to take a look at these molecules. One thing that we'll notice here is that we have an OH right here. So this is going to be pulling the electron density to the right. So this is going to make it polar. And we're going to be experiencing hydrogen bonding, or at the very least, dipole-dipole interactions, but most likely hydrogen bonding. All right. Then for the rest of these molecules, we see that we just have carbons and hydrogens, and there's nothing that is going to be pulling the electron density to one side or the other. So all these are going to be nonpolar. Okay, and if they're interacting with another molecule just like themselves, as they would in a kind of bulk matter property thing, they would all have just dispersion forces. So now we still need to rank these. So I'm going to start off by looking at the molecule that is polar and should be experiencing hydrogen bonding. And the one that is most comparable to that one is the one on the far left here, where we have the butane. So I'm going to label both of these as A for now. And the main difference here is that for the one with the OH, the butanol, this is adding an OH on there. And when it adds that OH, it is going to, essentially, it's replacing one of the hydrogens with an OH on it. And so this is going to, one, increase the molecular weight a little bit. Not a lot, so it's still actually quite comparable, but it's going to increase it a little bit. And basically, keep in mind, this is truly basically increasing the electrons, increasing the number of electrons. So that's going to be more polarizable because of that. And then the other thing is now it's going to allow hydrogen bonding. And so because of these reasons, and pretty much everything else is the same between these, this is going to have the higher intermolecular force compared to the butane here. The only difference is it has an OH versus an additional hydrogen on there, and so that makes it polar and also gives it a little bit more electrons to work with. So it's a little bit more polarizable as well. Now the next thing we can compare is the one on the far left, so our butane again, and the one on the far right. So I'm going to label both of these as B for now. And the one on the far left is butane, and it has the exact same chemical makeup. So C4, C4H10. And so this is going to be a little bit more elongated than the other one. So since it's more elongated, it's more polarizable. And since it's more polarizable, it is going to have these stronger intermolecular forces. So it's elongated. And so it's going to have essentially stronger intermolecular forces. So I'm going to label this as B1 and this one as B2. Again, I'm just giving one's the higher intermolecular force rating. All right, and then we have one more comparison we can do. So we have the one on the far right and the one right next to it. So we have this 2-methyl propane and comparing that with just straight up methane, CH4. And so with this one, they both have the exact same shape, except that the one on the far right has CH3s as opposed to hydrogen. So it's going to have more mass or has more electrons to work with. And it's also a larger molecule. All right, the CH3s take up a lot more space than just hydrogens, so it's going to be larger in size. And for these reasons, it is going to be a lot more polarizable, and so it is going to be higher intermolecular force-wise than the methane. So now we have kind of compared all these, and I'm going to go and start off with the butanol again. Since that one is ranked higher than A2, and we're going to go ahead and say this one has the highest intermolecular force. So if it has the highest intermolecular force, that also means it's going to have the highest boiling point. All right. Then we can look at the one on the far left, and it's higher than B2. And so this one's going to have the second highest intermolecular forces. And then for the one on the far right, this one is going to be the third highest IMF, or intermolecular forces. And then lastly, we have methane with the lowest intermolecular forces of this set. All right. So now we just need to rank them. It said we want to order molecules in increasing boiling point. So if we want to start off with the lowest boiling point, we're going to start off with the one that has the lowest intermolecular forces. And so this is going to be our methane. And then we're going to be increasing the boiling point, and we're going to go with the third highest intermolecular forces. So that's going to be the 2-methyl propane. All right, and then for the next highest boiling point, it's going to be the butane. And then finally, the one with the highest boiling point is going to be the butanol, because it has the highest intermolecular forces. All right, draw a little line there, and this will be the highest boiling point. All right, and so that's how we would solve that problem. All right, let's look at the next one. So based on the following information, where we have carbon tetrachloride, CCl4, with a melting point of negative 22.92 degrees Celsius, a boiling point of 76.72 degrees Celsius, and a molecular weight of 153.8 grams per mole, compared with carbon tetrafluoride, where we have CF4, a melting point of negative 183.6, a boiling point of negative 127.8. Those should be degrees Celsius. Sorry, that's not written in there. All right, and a molecular weight of 88 grams per mole. If both substances are at negative 200 degrees Celsius, which would have the higher equilibrium vapor pressure? So again, take a minute, see if you can figure that one out. Pause the video if you need to. All right, so let's go ahead and talk about this. So we need to find the highest vapor pressure. All right. So if we want to find the highest vapor pressure, that means we need to find the one with the lowest intermolecular forces. So when looking at these, we can see that the chlorines are going to be withdrawing the electrons from the carbon. And even though that's the case, this is a tetrahedral molecule, so it is extremely symmetric. So all the various components of the chlorines pulling off the electrons from the carbon essentially cancel out with the other chlorines. So we have the one over here on the left pulling the chlorines, we have the chlorine on the right pulling the electron density to the right, and then the ones that are going into the plane and out of the plane, if we add together their components for the essentially x direction, that's going to counteract that chlorine, the one that we had just looked at on the far right. And then the sum of their y components are going to counteract with the upper one that's pulling it that way. And then their z components are going to be counteracting themselves as they're going into the board and out of the board. So overall, even though we have chlorines pulling the electrons away from the center, this is going to be nonpolar overall. And so if we have carbon tetrachloride interacting with another carbon tetrachloride, the highest intermolecular force we'll have is going to be dispersion. Similarly, for the carbon tetrafluoride, all the electrons are going to be pulled towards the fluorines, but again, it's highly symmetric, so this is going to be a nonpolar molecule. And the strongest intermolecular forces between two carbon tetrafluorides is going to be dispersion. All right, so they're both having dispersion, so this is going to ultimately come down to which one is more polarizable, or which one has the highest polarizability. And so for this one, we have the CF4. It has less molecular weight, or fewer electrons, which is the truth of the matter. It has fewer electrons than the carbon tetrachloride. Also, CF4 is smaller than CCl4. And again, this is coming from the atomic size, where we have fluorine, and then down here we have chlorine. It's a little congested, but anyway, as we go down the periodic table and from right to left, both these things are going to be increasing atomic size. So the chlorines are going to be much, much larger than the fluorines. And so the overall molecular shape is going to be much, much smaller for CF4 compared to CCl4. So both of these factors make CF4, carbon tetrafluoride, less polarizable than CCl4, carbon tetrachloride, and thus having weaker intermolecular forces. All right, and since it has weaker intermolecular forces, this means that CF4 will have the higher vapor pressure. All right. Now, without really considering these other things, one could just look at the boiling points of both these molecules, and you'll see that CF4 has the lower boiling point, meaning that it also has the lower intermolecular forces, and it would have the higher vapor pressure. So again, boiling point is very indicative of intermolecular strength. So that is normally a really good thing to use. All right. So let's go ahead and go to our last problem. All right. Professor Dewberry is trying to prepare a demo for a class to exhibit interesting characteristics of intermolecular forces. He is trying to freeze a liquid in a test tube in liquid nitrogen, evacuate the vessel, and place a balloon over the test tube. He wants the balloon to blow up upon warming the sample to 100 degrees Celsius. but has had 3 failed attempts with 1 butanol, 1 propanol, and cyclopentane. For 1 butanol, it was underwhelming. For 1 propanol, it popped the balloon. And for cyclopentane, it also popped the balloon. Dr. Dewberry has only the following chemicals at his disposal. Which one should he pick to inflate the balloon enough for the class to see without popping the balloon? Label each with a prediction as underwhelming, pop the balloon, or potentially a good demo. Give the reason for each label. All right, so again, go ahead and feel free to pause the video if you want to try to figure it out for yourself. All right, so for this one, we need to look at these molecules and compare them directly. For this particular one, I didn't give boiling points, so you have to actually go through and compare them. So first we have the cyclohexane, and the cyclohexane is directly comparable with the cyclopentane. Sorry about that. All right, it's directly comparable with the cyclopentane. Okay. Now the main difference here is that the cyclohexane has an additional CH2 on it. All right, so it has an extra CH2 on it. And this is going to make it more polarizable. All right, so since it is more polarizable, it is going to have stronger intermolecular forces than the cyclopentane. Since it has stronger intermolecular forces, this means it's going to have a lower vapor pressure than the cyclopentane. And if it has a lower vapor pressure, this means that it might not pop the balloon. So lower vapor pressure may not pop the balloon. So in this case, we should label this one as potentially a good demo. We don't know, but we know that it won't inflate the balloon as much as cyclopentane. Okay. Now, when you want to look at the 1,4-butanediol, now this one is going to be comparable with the 1-butanol. All right, so it's going to be comparable with 1-butanol. All right, so both of these are going to be polar. All right, they're going to be pulling the electron density towards the oxygens, and with 1,4-butanediol, it can kind of twist around and rotate a bit, so it would be polar overall. because we can essentially rotate along these carbon-carbon bonds. And this one actually they would both exhibit hydrogen bonding. Now for the 1,4-butanediol, we have an additional, OH. As an OH instead of just a hydrogen at the end there. And so that's the only real difference. So this extra OH means it has a little bit higher mass or has more electrons. But it also means it has another site for hydrogen bonding. I'm going to creep over in this other space just a little bit. As an extra site for hydrogen bonding. And so both these factors, the extra electrons and also slightly increase in size, that's going to make it more polarizable. And since it has an extra site for hydrogen bonding, this is going to make it have higher intermolecular forces. So it's going to have higher intermolecular forces compared to 1-butanol. And if it has higher intermolecular forces, that means it's going to have a lower vapor pressure compared to the 1-butanol. And so this one's going to be even more underwhelming. So this is going to be more underwhelming than 1-butanol. And so since 1-butanol was already underwhelming, this one's going to be even more so. So it's still going to be underwhelming. All right, now for our last one, we have ethanol. Now, the one that we can compare ethanol with is propanol. All right, it's comparable with 1-propanol. All right, now the main difference here is that this one has one less CH2. All right, so that means it's going to have a lower molecular weight or has fewer electrons. And it's also going to be a little bit smaller. So this is going to make it less polarizable. All right, since it's less polarizable, that means it's going to have lower intermolecular forces. If it has lower intermolecular forces, that means it's going to have a higher vapor pressure. It has a higher vapor pressure than 1-propanol. So this one's going to essentially pop the balloon faster. Since 1-propanol popped the balloon, this one's going to pop it even faster. All right. Hopefully I can get my pen to work. All right, so that's going to pop the balloon even faster, so we're going to just label that as pop the balloon. All right. And so these are some questions that you might come across for intermolecular forces in, say, an exam setting. And hopefully this helped you out a little bit and gave you some practice. But that's all we have for today. So as always, keep thinking, and I'll see you next time. Goodbye.